Okay, good afternoon, everybody. So I think most people are here now, and we can start with the last session of this afternoon. So we're still learning a bit more about Post Lie algebras by Professor Dekimpe.
Yeah, sorry, I didn't hear you because my sound was off, but now I'm getting ready to start. So
okay, cool. Whenever you're ready.
Now you should see my blackboard. Is this okay?
Yes, we see it. Thank you.
Yeah, this is okay. This is okay. And yesterday was also okay. Yes, thank you.
I think yesterday it was a little bit out of focus, the blackboard, but
today's perfect.
Okay.
It's good that you put the focus on blackboard and light on the blackboard. So it was it is good now. It was me who commented the other day. So thanks.
Okay,
now it's good.
Good that things are working. So let me start where I ended yesterday. And of course, you're all very brave people also attending this last lecture. So thank you for this. So the last thing I showed was that if you have a pair of Lie algebras, Gn, where the G is simple or semi-simple, and this pair, this Post Lie structure, then the n cannot be solvable. So this means that actually I was able to put a lot of process, namely when G is simple or semi-simple, then I can forget anything which is solvable over here. And so from now onwards, I have to check these parts. So let me start with completing the row where G is simple. And actually, what I'm going to prove is that I can put two more extra crosses. So when G is simple, we can only have a Post Lie structure if n is also simple. And even more is true, G and n should be equal to each other, isomorphic to each other, and there are not too many products possible. So this is the first result for today. So let G now be simple and assume that the pair Gn admits a Post Lie structure then we have that n has to be isomorphic to G, so n is of course also simple as the algebra. And let me prove this. So the proof goes as follows. Well, we know that n, we can write this as the radical of n semi-direct semi-simple part, let's say S, and S cannot be trivial space because we know already from the theorem of yesterday that n cannot be solvable, so n cannot be the same as its radical. So there must be at least some simple part in the decomposition of n. And now remember the Post Lie structure. We can also view this as a map from n, from G to n to the derivations of n. Remember sending x to x comma left multiplication by x. And now you should also know that, let's say, if d is a derivation of n, then for any derivation, it holds that the derivation applied to the radical of n is sitting inside the radical of n. So the radical is always mapped inside the radical for any derivation. So this means that any derivation induces a derivation also on the semi-simple parts, just by taking quotient by radical. So it can always induces the derivation on the semi-simple part. So we do have a map, let's say P composed with L, where P is the projection from the derivations of n to the derivations of the semi-simple part of it, from G to derivations of S. And of course, S is a semi-simple part, so the only derivations we have over there are the n derivations. So this is just the same as S. Any derivation is just an n derivation. Now, since G is supposed to be a simple Lie algebra, and this is a Lie algebra morphism, there are only two possibilities for the kernel of P composed with L. Either this is the 0 one, yeah, or the kernel of P composed with L is the complete Lie algebra, because it has to be an ideal of G, yeah, and G is simple. So let me look at the two possibilities. So the first one is, let's say, the kernel of P composed with L is 0. So this means that P composed with L is an injective linear map and is an injective Lie algebra homomorphism. So certainly in this case, we have that the dimension of G is bounded above by the dimension of S, which is of course in itself so n is the radical plus S, so this is bounded above by the dimension of n, and we know that in a pair of Lie algebras, well, they are built up on the same vector space, so the dimensions are certainly the same. So as a conclusion, we get that all of these dimensions are the same. And so the dimension of S is the same as the dimension of n, which is only possible if the radical is 0. So from this, we get that the dimension of n is equal to the dimension of S, from which we get that n is isomorphic to S. And of course, also the dimension of G is the same as the dimension of S. So the dimension of G is equal to the dimension of S. And so this means that P composed with L is not only an injective map, but it's really an isomorphism. So it's an isomorphism from G to S, which is in its turn isomorphic to N. So as a conclusion, we get that indeed, in case the kernel is 0, that G is indeed isomorphic to N. So this is the first case. Now the second case. So the second case says that the kernel of P composed with L is the whole of G. So this means that the left multiplications induced on S are trivial, or this means that Lx applied to the Lie algebra N, yeah, has to sit inside the radical of N. Because if I quotient out the radical, I have to get 0. Yeah. So Lx maps is a derivation which maps N into its radical. For all x's, we have this. And now we have the following. So remember, we are looking at a Post Lie structure. So this means that the bracket of x and y, square bracket, minus the curly bracket. But let me write the curly bracket over here. It's the same as x dot y minus y dot x for any y at x. Now let me look at the following. Take the square bracket of G with the vector space, the radical of n. Let's take any x in G, any y in the radical. Then what I see is, well, certainly these products, yeah, these are left multiplications. Well, let me just write it like this. These left multiplications map everything into the radical. So this is an element of the radical. This is an element of the radical. Yeah, and the radical is an ideal. It's the radical of n, so it's an ideal of the Lie algebra n. So it's also sitting inside the radical. So this means that if I take the bracket of G with the radical, I end up inside the radical. And so the vector space, let's say, rad n is an ideal of G. And now we have again two possibilities. Either the radical of n is completely G, but if the radical of n is completely G, well, let me do two possibilities, or the radical of n is 0. Of course, the radical of n being completely G as a vector space that is being completely n. So this would imply that n is its own radical, and so n is solvable. Hence, we get a contradiction over here because our first result that we recalled from yesterday showed already that n cannot be solvable. In this case, the radical of n is 0. Yeah? And this means, actually, this means that if the radical of n is 0, so this means that all products are 0. So this means that x dot y is 0 for all x and y. And so this implies that the brackets are really equal. Yeah? So if the products are 0, the brackets are equal. And so certainly G is isomorphic to n, it's even equal to n. And so also in this case, the Lie algebra n and G are isomorphic as Lie algebras. Okay. So this allows me to pick my scheme again. Yeah. And so when G is simple, I have just proven that n has to be simple, and even more, they have to be isomorphic. Okay. So semi-simple is not possible, and reductive and not being simple is not possible. So when G is simple, the situation is really rigid. Yeah, n has to be simple. Yeah, and it has to be isomorphic to n. And in fact, we can even prove more. Yeah, I'm not going to put the details of what we can prove more. So, but in the case that G is simple, only very little possibilities are occurring. Yes. So suppose G is isomorphic to n, okay? And both the algebras, well, both the algebras are simple. Okay? So when Gn admit a Post Lie structure, okay, then there are only two possibilities. First possibility is either x dot y equals 0 or xy, and then in this case you have that xy is the same as xy. So square brackets are really the same as curly brackets. So this was the case I ended up in my proof of my theorem over here. Okay. And the second case, or x dot y equals, if I'm not mistaken, minus curly brackets xy. Let me just have a check. Yes, this is okay. And in that case, we have that the bracket of x and y is minus the curly bracket of xy. So these are the only two possible Post Lie structures of a pair of simple Lie algebras. So either the Lie algebras are the same, or one is what you could say minus the other one. The bracket is minus the other one. Okay. Nothing else is possible. Okay. So it's not possible to have anything else but this. Okay, and so I'm not going to prove this. It would take too much time, I guess. And we need the result for this of Jacobson. That's also quite deep, so I'm not going into details on proving this part. But we know that this is very limited. Okay, so let's go to the next line. And the next line is the case where G is semisimple. And so also here, I can formulate a proof, formulate a theorem, and I will formulate it without proof, although I will give some information later onwards. And this is not my result, but this is the result of Borde and his postdoc. I'm not sure if I'm going to spell the name correctly, Gubaev, but I guess both are present today. Yeah. So what is this theorem saying? Well, it says the following. Let Gn be a pair of, let's say, both semisimple Lie algebras. Yeah. Then Gn admits a Post Lie structure if and only if G is isomorphic to N. Okay, I have to give this proof without this theorem without proof. Their result is related to what is called Rota-Baxter operators, and I will tell a little bit if I have time, and I guess I don't have time, about the link between this situation and Rota-Baxter operators later onwards. Okay, so also in this case, this is more or less like in the simple case. If you know that both of them are, let's say, semi-simple, then you only have a structure when both of them are isomorphic. And so this means that we can not have a structure where G is semi-simple and simple, and not semi-simple, but not simple, and N is simple. So this case cannot appear. They should be isomorphic. It is, however, not as strict as in the situation for the simple ones. So if you take N and G isomorphic, semi-simple but not simple, then several possible products occur. So it's not true that these are the only two. Several possible products might occur in this case. I will leave this one open for the moment. So semi-simple and reductive, I will leave it open. And I go to the situation where G is reductive. So let me now tell a little bit about this case. By the way, this was a result which is quite recent. I guess the paper was published 2019 or 2020, something like this. So if my counting is still correct, I'm at 4.f. The case where G is reductive. Okay, and let me pick my system again. So I do not know too much yet in the reductive case. So I have shown you in the very beginning that reductive Lie algebras can have a left-symmetric structure. Yeah, remember, we just took matrix multiplication of GLN with itself. Okay. So, for example, the pair let's make it easy. GL to C, comma, the same vector space, but now considered as an abelian Lie algebra. So this is C to the power 4 admits a Post Lie structure. So, or GL to C admits a left symmetric structure. That's saying the same. Now, what do we also know? Yeah, we want to find something over here. Okay, and I want to make a combination such that my Lie algebra is still reductive. So what I'm going to use is I'm going to use an abelian G and nilpotent N. Okay? For example, you can use the Heisenberg Lie algebra, the three-dimensional one, which is two-step nilpotent. This has an LR structure. So this is the one over here. So this means that we have already seen. So let H, for example, be the Heisenberg Lie algebra. So this is the Lie algebra consisting of matrices of this form. So this is a three-dimensional one. Yes. Then, if I look at the abelian Lie algebra and H, well, this admits a Post Lie structure, which corresponds to an LR structure. Okay. And now we can combine this. We can combine the two using direct product structures. So from this, it follows that GL to C plus C3, comma, C4 plus H automatically also admits a Post Lie structure. Okay. And remember, this is just SL to C plus C, so this is SL to C plus C to the 4. So this guy is still reductive. And so this example shows that there is a Post Lie structure where this one is reductive and this one is nilpotent but non-abelian. So this means I have an example of reductive G and nilpotent and non-abelian N. And of course I can now do the same trick, yeah, by replacing the H with the solvable one. Yeah, for example, the two-dimensional solvable one and C2. We have seen that, yeah, in this situation we also had an example, and so we can use this one to really find an example of a reductive G and a solvable non-nilpotent N, and this pair has a Post Lie structure. Yeah. Okay. What about this case? Reductive and simple. Well, I have to rely again on the two guys, Burde and Bubarev. So in another paper, I guess, if I remember well, they tackled this problem. Yeah. And they actually could show that in this situation, G reductive and simple, reductive not being semi-simple, that there is no structure possible. So using more or less the same approach, using Rota-Baxter equations, they could prove this situation. And so this means we are left with two more cases, namely the case where one of the two Lie algebras is reductive and the other one is semi-simple. And the actual situation up to today, up to my knowledge, is that we do not know. So these are, maybe you cannot see this, but I'm writing question marks. So these situations, we do not know the answer. Yeah, we have no idea whether or not there exist examples over there or not. Yeah. So this is the table as we know it now. But to be honest, we had one more condition that we investigated, namely the condition of complete the algebras. And so we can also fill up the table with the structure complete, but it would lead me too far to also treat these cases. Yeah. So that's the situation up to today. And so if anybody of you finds a solution to one of the two question marks, we would be very happy. But of course, we will be trying to solve this too. Okay, so what I now would like to say is a little bit about how Buddha and Gubarev approached the problem of Post Lie structures using Rota-Baxter equations. And so let me call this a small point 5. So 5 is Post Lie structures and Rota-Baxter operators. So first, the definition of a Rota-Baxter operator. So let A dot be a non-associative algebra. So just for me, an algebra would have to be associative. Then a linear map R from A to A is a Rota-Baxter operator. Of weight lambda, if and only if we have the following: for any x and y in A, it should hold that R of x times R of y is the same as R of, and then R of x dot y plus x dot R of y plus lambda times xy. So this weight, yeah, this is just an element of the field over which your algebra is defined. Okay? And so this is what is called a Rota-Baxter operator of weight lambda, and there has been a lot of investigations around this Rota-Baxter operators, of which I'm really not an expert. So this is the reason why the other people have tackled this problem. But anyhow, I would like to explain you a little bit how these Rota-Baxter operators are related to Post Lie structures. And so in my situation, I will not look just at a general non-associative algebra. For me, a dot will be the Lie algebra n. So I will have n, and the product will be square bracket, curly brackets. So this is my algebra. And then if I look at the definition of a Rota-Baxter operator. So this means that the product of those two, so this means the read bracket of those two, should be equal to R of the product of R of X and Y plus X R of Y plus the product, plus lambda times the product of XY. And so this is a Rota-Baxter operator on the Lie algebra and curly brackets. And let me keep this on the blackboard, because now I'm going to start with my Lie algebra and do some stuff with it. So let's n again be semi-simple. Recall we use this stuff in the situation where n was semi-simple. And just suppose also that Gn admits a Post Lie structure. Or maybe let me just keep it more general. Suppose that dot is a product, binary product. Such that n, comma, the Lie bracket, comma, dot is a Post Lie algebra. And then I know that the square bracket is defined using the curly bracket and the dot. So what do we know? We certainly know from the conditions, the last conditions of a Post Lie algebra. We know that each L of X is a derivation of the Lie algebra n. So this is actually one of the defining conditions of Post Lie algebra. But since n is semi-simple, we know that all derivations are n derivations. So this means that L of X is actually the adjoint of phi of X for some map. It has to be linear, otherwise the product would not be bilinear. For some linear map, phi growing, let's say, from n to n. So x dot y can be written as phi of x y. It has to be the adjoint of phi of x applied to y. And of course, the adjoint in the Lie algebra we are working with. Now, what can we do? Well, consider now any linear map phi from n to n, and now we can investigate when does such a map and this product, so when does the dot defined as above, when does this define the Post Lie algebra structure or Post Lie algebra above? Okay, what do we have to check? Well, remember the definition of a Post Lie algebra from my first class. I needed that this was a Lie algebra, that I'm assuming. I needed that left multiplications, that was the condition, are derivations. I'm supposing this. And so the only thing I have to check is the condition that if I look, so the condition I have to check is that this applied, so curly brackets dot z should be the same as, if you remember, the associative of y, x, z minus the associated of x, y, z. So this was the condition. Okay. And now I'm just going to compute what this means. So let me start with the left-hand side, which is rather quickly done. So the left-hand side is, well, I have to take the product, the curly brackets of phi of the first component, comma y. So phi of the first component, comma the second component. The right-hand side, so the right-hand side, the associated was x dot y dot z minus x dot y dot z minus the associated with x in front. And now let me make the computation. So this is phi of this product, comma z, and this product in between is also phi of y, comma x. So this is the first one. So phi of this comma z, and this product is this. Okay. Minus, so this is phi of x, comma, another product, the second one, and the second one is phi of y, comma z. This one, this becomes minus phi of x, comma y, comma z. So the same one as this one, but x and y reversed. And now plus over here the same thing. This is wrong. This should be yx. Yeah, just the associated, just replace brackets. Yeah. And so this should be phi of x, comma, phi of y, comma z. Okay. And now let me have a closer look at these two terms. Okay. So I have phi of x, phi of y, z. I have phi of y, phi of x, z. We have 3 times the same terms, but permuted. Okay. And actually, I can write this one as plus, and maybe, so I will, so this guy minus this guy is plus, and I interchange the positions of the two. So this is the same as this one. And now I see I have phi of x, phi of y, z, phi of x, phi of y, z. So if I add well, I can use Jacobi identity now. So let me keep writing it, what I have. So the right hand side, let me just take these factors back. So this is phi of y, comma x, comma z. I take this factor minus phi of phi of x, y, and now using Jacobi, yeah, this one plus this one plus the other one cyclically permuted is 0. So I can here take minus the other one cyclically permuted. So this is minus z phi of x, phi of y by Jacobi. So this is the right hand side. Okay. Now, of course, I can now interchange the position of these two. So forget about this factor and write plus 5x phi of y z. And now, as a conclusion of the computation, I get that the right-hand side should be equal to the left-hand side, and the left-hand side is phi of xyz. And now you see this is a bracket applied to z, this is a bracket applied to z, this is a bracket applied to z, and this is a bracket applied to z. So in total, if I would group everything together, I will get something of the form. This comma z has to be equal to 0 for all z. If I put this one on the other side and I group together, I get this condition. Now, as n is semi-simple, its center is trivial, so this can only be 0 if this factor is 0. So I can't forget about the z's. And so I get that my product is a post Lie product if and only if this part and this part and this part equals this part. And now let me put it a little bit on the right side to get what I want. So I leave this one where it is. So I get that phi of x, phi of y should be equal to. So this one is on this side. This one is also on this side. So let me put this one already over here. I have to move this one to the other side. So this is minus phi of phi y comma x. I have to put this one on the other side. So this is plus phi of phi x comma y. And now I can group these three together and put phi in front. This one is with the plus sign, so let me write it. This is phi of x comma y bracket. Let me change these two in place so that I get a plus sign. So this is plus x phi of y, and then this is just the bracket which is left over plus xy, and so this should be equal to phi of x phi of y. And now, if I did not make any mistake, if you look at this expression over here and you look at this expression over here, this should be the same when you replace the r with phi. So this is phi of x phi of y, apply phi to all of this, so it seems to be the same with lambda equal to 1. So as a conclusion, we get that post Lie algebras products on, let's say, a semi-simple the algebra in curly brackets correspond to Rota-Baxter operators of weight 1. Yeah. Okay, and that's all that I'm going to say about the connection between the two. If you want to see how this has been worked out, again, there's one good place to find all the information. Go to the Budrev's website, and look at his papers together with Gubarev, and you will see how it works. So they use this in a quite ingenious way to prove the results that I mentioned before. or you can ask them later on because they are hopefully still present. Okay, so what else can you do? Yeah, so I have 10 minutes left. Let me use this, or 15 minutes left. Let me use this to say very briefly what else we have been doing on the post Lie algebra structures. And we have been studying what is called commutative post Lie algebra structures. So sixth and final section is about commutative post Lie algebra structures. So as the name already says, commutative post Lie algebra structures, these will be structures in which the product is commutative. So these are post Lie structures. Product so the product x dot y has to be equal to y dot x. This is commutative. And so, of course, what we get is that xy minus curly bracket xy has to be equal to x dot y minus y dot x, which has to be 0. So in this situation, we always have that we are working on one Lie algebra. So we will be talking about commutative post Lie algebra structures on a given Lie algebra. And we mainly now use square brackets. This is because square brackets are more often used for Lie algebras. And so the definition could be definition a commutative post Lie algebra structure on a Lie algebra G, and let me indicate the brackets, is a bilinear product such that, of course, it has to be commutative. -1 is 0 or they are equal. And then this condition is automatically satisfied because it's square brackets minus square bracket. Then just the second condition stays. So this has to be x dot y z minus y x z. And the third condition also stays, but now I do not have to make a difference between square brackets and curly brackets, so it's only one bracket involved. And so these are the conditions for a commutative post Lie algebra structure. And it turns out that this might sound a bit trivial to investigate this, but nevertheless, one can prove nice theorems and nice results about this. And so I want to mention just one result that we proved in this direction, just as, let's say, a hint of what we have been doing. And this is actually an investigation which is still going on. So there's still a lot to do, even in this more or less easy case where G and N are the same Lie algebras. So just an example of results. And the result says the following. That n, well, that g, let's say, g nilpotent Lie algebra such that the center of G is sitting inside derived subalgebra of G. And I will comment a little bit on this condition later on. Then, if dot is a commutative Post Lie algebra structure on G, or said otherwise, is a Post Lie algebra structure on the pair GG, the same pair, then for any x in G, it holds that left multiplication is a nilpotent map. So all maps have to be, all left multiplication maps have to be nilpotent maps. Yeah. And so, for example, this means that if you, well, it's too much work, but we can prove that this will imply that G dot G, yeah, will always be smaller than G and so on. Okay. This is one of the kind of results that you can prove. Of course, you can use this information then to construct all possible commutative Post Lie algebra structures on a given Lie algebra. This is a beginning to start constructing them. Now I want to mention a little bit about this condition. Yeah. Is this a strong condition or not? Well, this is not really a strong condition because if you have nilpotent Lie algebra, then G is always of the form an abelian part plus G prime. And we have that for G prime, this condition is satisfied. So you can always write it as a Lie algebra, and the nilpotent Lie algebra satisfying the condition plus an abelian part. And so this is the part of the center which is not sitting inside G comma G. Okay? And the condition is really necessary. Yeah? For example, if you take just if G is just take any field, for example C, yeah, and so you define it as the vector space on one basis vector, and you define the product E1 dot E1, yeah, to be equal to E1. Well, of course, then L of x, yeah, is not nilpotent. It's the identity map over here for E1, yeah. But this will be a commutative Post Lie structure, yeah, on the one-dimensional Lie algebra. So we really need the condition, yeah. And on this part, you can always do something which is non-nilpotent, the left multiplication maps. On this part, the left multiplication maps have to be nilpotent. So this gives us information on how to construct these kind of results. Yeah. Okay, and this was just an example of what we have been doing. I should mention that this is a result together of B. Dietrich and Wolf van Moens, yeah, and we published this a few years ago. I forgot the exact date. So I guess I will stop here, and I thank you once again for your attention.
Thank you very much. Are there any questions?
Yes, I have.
Okay, please go ahead.
First of all, I wanted to thank you, Karel, for this really nice lectures. And thank you for for presenting all these results, and it was really great to see this poster. You know, this was very nice with the existence. And also, I want to make a small comment, since Seva Gubarev is also there, that actually this question, if both are semi-simple, we haven't solved completely, but actually it was you who pointed out how to close the gap which was still there. But so you are very modest. So actually, I think we have now solved it.
Yeah, okay.
And the case with reductive, I guess, is...
We will solve this next week, Dietrich.
Sorry?
We will solve this next week.
All right. This was my question, but it is then clear. So thank you again for presenting these nice lectures.
You're welcome.
Anybody else?
Okay, I would thank Professor Karel for the good talk, representing the one generalization of Lie algebra, and this participant appreciates especially the white poster with 6 times 6 matrix. So it's a very pedagogical.
Yeah, so thank you for
very much. Okay, thank you.
You're welcome.
Any other questions? Then I would think we thank the speaker for this excellent series.